Welcome to our lecture for today. Today we're going to do chapter 8 in the textbook of Cengel and Ghajar, and the lecture is on internal forced convection. Right, internal forced convection has many applications. And the applications are usually of liquid and gases. Liquid and gases that flow through ducts and pipes. Let me see if I can do something about this sound. Okay, I hope it's better now. Okay, and when we have these flow through ducts and pipes, usually it is in applications where we have heating and cooling. And the heating and cooling normally occurs in heat exchangers. And before you can get to heat exchangers and understand heat exchangers, you actually need to understand the heat transfer firstly through tubes and pipes and ducts. First start very simple. Now usually in these cases we have forced convection. Okay, what do we mean with forced convection? With forced convection normally occurs when we have a pump or a fan that will ensure that flow occurs through the pipe or the duct. So it is not only the purpose in this chapter to look at the heat transfer, but in all cases we actually want to connect it to the pressure drop also. So therefore, we also need the friction factors. So in general, we are always interested in the friction factors and the Reynolds numbers. Right. With the friction factors, we can determine the pressure drops and also the power required by a pump and a fan. Okay, so the power required in watts or kilowatts or whatever. With the Reynolds number, we can get the heat transfer rate. So that's the reason why we need the Reynolds number. Right. Now in chapters 7 and 8, the question can now be asked, but what is the difference between the two chapters? Both of them are on forced convection. Well, chapter 7 was on external forced convection, while chapter 8 will be on internal forced convection. Okay. Now again, so what? Why is that so important? The reason for that is that with external forced convection over any body, although I'm drawing a flat plate here, it might be a train or aeroplane or whatever. On those bodies, the boundary layer will develop. And there will be two types of boundary layers. There will be a boundary layer for the velocity distribution, and there will be a boundary layer for the thermal distribution. So there will be two of them, and we are going to discuss them just now or with the next lecture. And they can grow infinitely. Okay, so they can become very, very thick. While with internal forced convection, the boundary layers are, of course, limited by the two boundaries. The boundary cannot be more than the upper boundary. You agree? And normally what will happen is this boundary layer will grow, and that one will grow, and they will meet each other. And that is the difference between external forced convection and internal forced convection. Okay, so again, there are two boundary layers, one for the velocities and one for thermal, and they will meet at the stage. And when they meet, something unique is going to happen, and we're going to discuss it just now, or a little bit later with the next lecture. Now with both of these types of problems, the heat transfer rate, if I say the Reynolds number, I mean the heat transfer rate. Okay. So with both of these problems, the heat transfer rate is a function of, firstly, the Reynolds number, the flow over the body, the speed of it, or the mass flow rate, or the type of liquid. It will depend on the Prandtl number, which has to do with the characteristics of the fluid, the Cp, the viscosity, and the thermal conductivity, and a number that I think you haven't seen before, the Grashof number. So with both of them, the Nusselt number is a function of the Reynolds number, the Prandtl number, and the Grashof number. Right. Now, because we have to introduce the work very systematically to you, the Grashof number is not going to be discussed already now. We're not going to introduce it in this chapter. It's going to happen in the next chapter on natural convection. But this Grashof, well, let me first just look at all the non-dimensional numbers, and then I'll explain to you what the Grashof number is all about. Okay, so let's start with the Reynolds number. The Reynolds number, as you know, is equal to the velocity, the density multiplied by a velocity multiplied by a characteristic length divided by the viscosity, and it is the ratio of the inertia forces to viscous forces. Okay, inertia, we mean the velocity. Viscosity, we mean, with viscous forces, we mean the viscosity. Okay, the ratio of those two forces. Okay, so that one you already know, I'm sure. Then we have the Prandtl number, which is equal to μ multiplied by Cp divided by K. The viscosity multiplied by the specific heat, Cp, divided by the thermal conductivity of the fluid. So those three together will make up the Prandtl number, and it gives us the relative thickness of the velocity and thermal boundary layers. So very shortly, let's say it is the velocity boundary layer divided by the thermal boundary layer, the relative thickness. And it has to do with how quickly heat can be dissipated through a fluid. So that is what the Prandtl number tells us. Okay, and you will see in general that if the Prandtl number is approximately equal to 1, then the heat diffuses approximately at the same rate than the momentum diffuses. Okay. If the Prandtl number is smaller than 1, then the heat diffuses quicker. And if the Prandtl number is larger than 1, then heat diffuses slower. Okay, now at this stage you're not really going to understand what I'm trying to say here. But just be a little bit more patient. If we don't finish it with this lecture, we're going to address it with the next lecture. So that is what the Prandtl number tells us. The other number now is the Grashof number, and that one is equal to G multiplied by beta, which is the volume expansion coefficient. Again, we will do that in the next lecture or the next chapter, multiplied by the surface temperature minus T infinite, divided by the viscosity square. Oh yes, and there's an L to the 3. Okay, and that number gives us the influence of buoyancy. Buoyancy, okay, natural convection. As you're in this lecture venue, there's not really a lot of forced convection. But because you give off heat and gravity, the result will be that there are flows, very, very low velocity flows in convection in this room. And this might also appear inside bodies in which we have internal forced convection. But for this chapter, we are going to not consider those effects. Okay. Any questions up to now? Nothing, right. Paragraph 8.1 is the introduction. Okay, and it starts with terminology. Terminology. And it's about the terminology between pipes, ducts, and conduits, which are being used interchangeably. But in general, we use the following terminology. So if we have a tube with a cylindrical type of geometry, so it's a cylinder, then we will call it a pipe or a tube. Okay. Now the terminology internationally between what is being considered as a pipe and a tube differs a little bit. So in some textbooks they would say that if the diameter is very large, okay, then we will say that it is a pipe. While if it is a small diameter, it is considered as a tube. Okay. And in other literatures, they would look at the relative roughness. And they would say that if it is a very, very smooth tube, if the relative roughness is very, very small, then we will say it is a smooth tube. And if it is rough, we will say it is a pipe. Okay. However, if you're going to work in industry now and you're going to work with pipes and tubes and whatever, these days almost all tubes or pipes, whatever you want to use, if you go and measure their surface roughness and you divide it by the diameter, you will find that for all practical purposes they're all smooth. So the epsilon divided by d for all practical purposes is approximately equal to 0. And the reason for that is that all tubes these days are soft-drawn tubes or hard-drawn tubes. So the technique is different than 50, 60, 100 years ago when they were casted. Okay, and then they were very rough. But these days, it doesn't happen a lot. Okay, then ducts. What do we consider as a duct? That's a cylindrical pipe or tube, and these will be ducts. And that will be a geometry like a square, one like that, or typically like that. Where do you get that? You get that typically in the heating, ventilation, and air conditioning industry, where buildings are being air conditioned. Normally they are galvanized sheets which are being bent, and normally the pressures typically on the inside, the maximum pressures that it can take is approximately 120 kPa. So if atmospheric pressure is about 100 kPa, they can take pressure drops in the order of about 20 kPa. Why? Because usually they are very big. And because the area is so large, the forces are very, very large. Okay. Now pipes normally can take very, very high pressures. So in pipes we will normally get fluids, and a geometry like that can take very, very high stresses, in the order of megapascals, very, very easily. Okay, so megapascals, while here we are in the order of kilopascals. So that is just general terminology. Where we also get these types of geometries these days are in microchannels. Okay, microchannels are being used in electronic components to cool components these days. And it is much more easy, or it is easier to manufacture a channel like that than that. Okay. Right, paragraph 8.2 is average velocities and temperatures. average velocities and temperatures. Let's consider a pipe, a tube, or a duct. Doesn't matter. And I'm going to draw it quite long because I need some space here, like that. Let's suppose there is the pipe or the duct. And here at the inlet, that is the inlet velocity. And I'm going to choose a velocity of 0.01 meters per second. And the duct or tube diameter is 150 millimeters. 150 millimeters. Okay. Now what is going to happen here at the inlet is that this velocity is equal to 0.01 meters per second, and then it is going to be exposed to the wall. And the moment it is exposed to the wall, there's going to be viscous forces, and the velocity on the wall is going to be 0. Okay. And the result of that is that a boundary layer is going to develop. And I'm specifically going to use blue. So if you've got a blue pen and a red pen, use the blue now and the red for temperature. Right. So what is now going to happen is the boundary layer is going to develop. And that is the development of the boundary layer. And that distance is delta. Okay. It's going to be in my way a little bit there. Okay. Let me do it here. Okay, so that is the boundary layer thickness, delta. Okay. So what is going to happen is that the velocity distribution, if the flow is laminar, and that you've already done in fluid mechanics, my sketch is not so good. Okay. Something that's here is very important is if you look at this distance, there is it, multiplied by 2. That is where I should end. Okay. So look at this distance, that one, 2 of them. Okay. So the velocity profile is going to be that of a parabolic, like that. Okay. And what's very important is 2 things of that velocity boundary layer that developed. And you've done that in fluid mechanics. Okay. This distance is the average velocity. Okay. That is the average. And this distance is V max. And V max is equal to 2 times the average. Okay. So that velocity there is equal to 0.02 meters per second. You agree? Okay, so what I start with here, because of the fact that continuity must still occur. I mean, what you're putting in must come out. And that mass flow, now because of this change in the boundary layer, so what is going to happen here? In this part here, you're going to get the part which is irrotational flow. Irrotational flow. There's no other forces. It is like ideal flow. It doesn't even know about the boundary layer. So here it will still develop at that, and you're going to have a boundary layer that typically looks like that, a velocity boundary layer. Okay. But at the end, it has to be squeezed so that we end up with the boundary layer looking like that. Right. Now, in terms of terminology, what I'm going to do is, that is going to be R from the center, and the radius of the tube is going to be capital R. So capital R is equal to 75 millimeters. You agree? So Vmax, that velocity there, Vmax will be equal to 2 times V average, which is equal to 2 times the inlet velocity. Okay. So this velocity here, this average velocity is not going to change. It stays a constant. But the maximum and this profile is going to change to something like that. Right. Now in fluid mechanics you have derived the following equation. The velocity, small u as a function of r, is equal to Vmax multiplied by 1 minus small r squared divided by capital R squared. It's equation 1. Later on we're going to use that equation again. Okay, and Vmax is equal to 2 times that velocity is equal to 0.020 multiplied by 1 minus r squared divided by 0.075 squared. Okay, so that gives us the velocity at any point where we want to go and calculate it. You agree with me? Any questions? Okay. Let's, for example, if you would like to be interested in, well, that is 75 millimeters, and there's about 50 millimeters. So let's choose that point there. Okay, and we call that point the velocity at 50, U50, where R is equal to 50 millimeters. Okay, so then you can see that we can calculate the velocity at 50 millimeters by just putting it into this equation, 1 minus 0.050, just to get it in meters per second, divided by 0.075 square. And the result would be equal to 0.0111 meters per second. Okay, so that is the velocity distribution. So you have been given the tools in fluid mechanics to tell you exactly what is going to happen there. But take note, it is only for after the flow has been fully developed. You do not have the tools to go and calculate it there. You agree? So it is only after it has been fully developed. Okay. Now, why did I choose this stupid value? Why didn't I just choose 2 or 3 meters per second? Well, there was a good reason for that. And that is, let's just calculate the mass flow rate. So the mass flow rate through the tube is equal to rho multiplied by the cross-sectional area multiplied by the average velocity from fluid mechanics. Right, the density let's choose water. I've chosen water for this problem. Multiplied by the cross-sectional area, pi divided by 4, 0.150 squared, multiplied by the average velocity, which is equal to 0.01. And the result is a mass flow rate of 0.01767 kilograms per second. Let's check the Reynolds number. The Reynolds number is equal to rho Vd divided by the viscosity. The density, I've chosen water at 1,000 multiplied by 0.010 multiplied by the diameter of the tube, which is 0.150, divided by the viscosity of water. Let's suppose it is about at 20 degrees Celsius, so it will be approximately 1 multiplied by 10 to the minus 3. So, the Reynolds number is 1,500. That's very important. So I've chosen it specifically that the flow is laminar, because this is only valid for laminar flow, not for turbulent flow. If the flow is turbulent, the velocity would have been constant almost right through at 0.01 meters per second. There wouldn't be a velocity distribution. Okay. Now let's start making this problem a little bit more difficult. So the same physical problem, the same tube, there it is. And again now in blue, the velocity boundary layer, there it is. And I'm going to draw it in blue like this. There it is. And that is because of, so that should about be two distances like that. So about that distance there. So there is the inlet velocity. And that is the boundary layer thickness delta. Right. Now, on this same problem, what I'm going to do now is, let's heat the wall. So the surface is now equal to 100 degrees Celsius of the pipe or tube all over. So it's a constant, Ts. Surface is 100. And now the inlet temperature is going to be 20 degrees Celsius. Now temperature is not a vector, so I cannot draw an arrow. But what I can do is I'm going to draw a distance. And let's suppose that is about 20 millimeters in length, or 200 millimeters in length. So my inlet temperature of the water is 20 degrees Celsius. I hope you can all read the colors here. Is it okay? Ti is 20 degrees Celsius with a red. Okay, and again, this is going to be 0.01 and 0.01, so that velocity there, maximum velocity, will be equal to 0.02 meters per second. So the fluid mechanics, we've got it, and we can calculate all we need. Right, now, how is the temperature profile going to look like if I now heat the water? If I heat the water, I'm going to end up with a profile like this. And okay, so let's suppose that is about 100 millimeters, shows the temperature, okay? And here's the temperature in the middle, maybe approximately 20 or 20 degrees Celsius. So if I can measure the temperature at different places, then the temperature profile is going to look something like that. Okay, now I didn't want to make a mess and try to draw this on top of that, but that is actually the idea. Okay. Okay. So that is typically the temperature profile. Let's suppose that length there is 100, and that length there in the inside is approximately 20. Now, my question to you, ladies and gentlemen, is what is the average temperature in the tube at a specific place? What is the average temperature? If you have the velocity profile. So I give you the velocity profile. I'd say it is laminar flow, and you know it is a parabolic velocity profile. How are you going to get the average now? So that is what this part of the textbook is all about. Right. Now, if you think about this for a while, I think you will agree with me that you cannot just say, well, let me take 20 and 100 and say it is 60. Okay, it's not really going to work. Why? Because the velocity there and there are not the same, you see. The velocity we need to take into consideration, but the velocity is also actually the mass flow rate. So if we think about this a little bit and we actually make this tube a little bit larger, and we look at this temperature profile here on the inside, looking something like that. Okay. What I can do is I can say, well, if I know the temperature profile, which, so by the way, is now a given thing, so I give you the temperature profile and I ask you what is the average temperature. So what you can do is you can say, well, let me be very critical about it and think about it for a while. So what I can do is I can say, well, let's suppose the temperature there is 100 and I look at where the temperature is 90 and maybe 80. Okay. And that diameter is D1, that diameter is D2, and that diameter is D3, etc. D1, D2, D3, etc. So, I think, I don't know what you think, but it wouldn't be too bad an assumption to say, well, let me look at this part of the problem. Okay, that one there. And I say, well, the average temperature should be equal to, let's say, this temperature there, 95. Okay, 95, multiplied by the mass flow rate through that part. You agree? So let's call it the mass flow rate through section A. And that is section A. Plus, I look at this part and I say, well, temperature about 85. 85 multiplied by the mass flow rate through this part, which I call B. Etc. Okay. And then divide by the total mass flow rate. So it is a weighted average based on the mass flow rate. You agree? That would be quite an accurate way of calculating the average mass flow rate. And the mass flow rates, obviously, we can say it is equal to rho multiplied by the velocity, and it will be the velocity at A, there. Okay, multiplied by the cross-sectional area at A, plus 85 multiplied by rho, the velocity at B multiplied by the cross-sectional area of B. Okay? And then I can write the area as 95 multiplied by the density, multiplied by the velocity at point A, multiplied by pi divided by 4, d1 square minus d2 square. Okay? All fine with me? All with me? Plus the next one, 85, multiplied by the velocity b, pi divided by 4, d2 square minus d3 square, etc. Okay? This mass flow rate, of course, the mass flow rate of A plus B plus C, etc. Okay. And I do have the equations to calculate the velocity distribution. Here it is. Do you see? Here is the equation, if I go back to it, where we've written what the velocity distribution is as a function of r. So for every one at point r I've got, and I can go and calculate it. Okay, so that is the background to it. Are you all finished with it? Can I clean it? Anybody still busy? Did somebody say yes? I'm writing out, so I'm sort of out of board space at the moment. Okay, so the mathematical way is to say, well, what I've been doing there is actually to look at the energy which is being transported by a fluid, taking into consideration the mass flow rate. So it starts with the energy going into the fluid, which is equal to mass flow rate Cp multiplied by Tm. And Tm will be the average at any specific point, the mean temperature. Okay, so Tm is a function of x, but is the average temperature at a specific point. Okay, that is going to be equation 2. We're going to use it later. Okay, now we can start writing this into an integral form, saying it is the integral of integrating over the mass flow rate multiplied by Cp multiplied by the temperature, which is a function of R, multiplied by delta M dot. Okay, so it takes into consideration the temperature as the function of R, and the mass flow rate, we can write it as rho multiplied by the cross-sectional area multiplied by the velocity. And if you go and clean it up a little bit, you're going to see it is equal to the integral of integrating over the area multiplied by Cp Tr rho UR dAc. We're almost finished with it. Every step of the mathematics, don't worry, you don't have to understand it. You just need to understand where it comes from. Okay. Now, we're going to make an assumption, and a very important assumption. You have to remember when you get to this equation, and that is that we're going to make the assumption it is a circular tube. Okay, so A, like that, is always an assumption that I'm making. So the assumption is a circular tube with a diameter d, or 2r. Okay. Now when we've got a circular tube, you know that the cross-sectional area, if we want to do the integration from 0 to r, is equal to 2 pi r dr. Where does it come from? Well, from the fact that if I integrate this, it will give r squared divided by 2. Okay? And if you replace the r in it, then it works out as pi r squared. Okay, so putting that back into the equation gives us then the energy going into the fluid, the integral from 0 to r. Okay, we want to do the integration over the radius now of Cp Tr rho Ur 2 pi r dr. Okay, and we still need to remember from equation 2 that this is actually equal to the mass flow rate Cp multiplied by Tm. We actually want to get Tm is then equal to the integral of 0 to r of Cp, the temperature as function of r, rho Ur 2 pi r dr. Okay. And now, remember, that is from equation 1, where we've got the velocity as a function of r is equal to 2 times the average velocity multiplied by 1 minus small r squared divided by capital R squared. And if you put that in there and clean it up a little bit, it is all in the textbook, so you can go and do it at home, and making the assumptions that the viscosity and Cp are constants. Okay. I don't expect of you to be able to derive this equation, you just need to know where it comes from. Then we can derive that the mean temperature is equal to 2 times V average multiplied by R squared, the integral from 0 to R, Tr Ur r dr. Okay, and that is equation 8.4 in the textbook of Cengel and Ghajar. Right, so just take a good look at it quickly, and then I'm going to just clean the board on this side. Right. Now coming back to this example, I've given you a specific example of the velocity distribution which is equal to that. Okay? So it's still valid. So for this problem, as an example, we still have that the velocity as function of r is equal to 0.02 multiplied by 1 minus r squared divided by capital R squared. Okay. And what I'm going to give you now is the temperature distribution, an equation for the temperature distribution. This is not a derived one. This is just one that I've chosen myself, an arbitrary one. Okay. And this one looks like this, minus 80 multiplied by minus a quarter minus r squared divided by capital R squared. And for both of them, we have to do the integration to the radius, a radius of 0.075 millimeters. Right, so who of you want to do the integration for me? Okay, so it is simple, isn't it? It's just this equation multiplied by that equation multiplied by an r. Okay. Marlies tried over the weekend and she said, no ways. That is why there's numerical programs, and she did it for me, and the result was that for this case, the temperature would be 46.7 degrees Celsius. Okay, so do you all understand? Okay. So getting the mean temperature in a tube where we have a temperature distribution in it is more complicated than for the velocity distribution. The reason is the velocity distribution, obviously, the mass flow rate in terms of every control volume, the contribution of it is being influenced by the velocity distribution. Any questions? Okay. Right, let's look quickly at laminar and turbulent flow in tubes. You should know it, but just a little bit of revision. If we have flow through a tube, okay, and the flow, all the particles are parallel to each other, like that. It's like streamlines or laminates. That's where the word comes from. So streamlines or laminates, then the flow will be called laminar flow. Okay. However, if the flow is more chaotic like that, then the flow is turbulent. And we've got transition in between the two, which is quite a complicated velocity regime. So, if we take measurements of the laminar flow regime and the turbulent flow regime, we will get the following characteristics. If we take it with the best possible instrumentation, very, very accurate, and we measure at a specific point, let's suppose that point there, that's my measuring point. If I go and measure the velocity, it will be an absolute constant. There will be no variations in the mass flow rate or in the velocities. Will be perfect constant. Okay? Well, if the flow is turbulent at a specific point, then the average will be constant. However, on that average value, we will have all these fluctuations of the velocity. Okay, something like that. And if we look at the pressure drops as a function of R, so if we go and measure the pressure drops, then we will have something like that, F divided by 64 in the laminar flow regime. Then we will have a regime of transition and then a regime of turbulent flow. So that would be laminar, that would be turbulent. Okay. And the transition would typically occurs at a Reynolds number of approximately 2,300. Okay. Where will the flow again be fully turbulent? Well, it depends on many things, unfortunately, but in the region of approximately 4,000 to 10,000. So if the Reynolds numbers are higher than that, then normally the flow would be turbulent. However, if the tube inlet is extremely smooth and there's no vibrations on your experimental setup, transition might only occur at a Reynolds number of up to 100,000. Okay, so it's not a fixed value. But in general, you can work with approximately 2,300 to 4,000. Now that's the friction factors. If we look at the Nusselt numbers as a function of Reynolds number, then if the flow is forced convection, it should all be a constant, and I'm going to show it to you later on, up to the point where we get transition, and then from there on we will get the turbulent flow. So it would look approximately something like that. Okay, so the flow regime, as you can see, has a huge influence on the friction factor, the pressure drops, and the heat transfer rate. I see I'm out of time, ladies and gentlemen. So thank you very much. Marlies, you can cut.